Let us start. First, I forgot to mention last time, I will always use the metric convention for Minkowski space-time to be given by this one. So the time component have -1, and then the spatial component is +1. And yeah, so also let me just first remind you what we did in last lecture. So in last lecture, we talked about principle of locality, which is a powerful principle. And so this naturally leads to the concept of fields. And so I will generally denote fields, say, using this kind of notation. Yeah, in the when we talk about fields abstractly, we will use this kind of notation. And so phi just and A just label for different fields, and also so the fields depend on spatial coordinate and also depend on time. So physically, you can think of this spatial dependence as the label for the fields for the degree of freedom. So at each spatial point, there is a degree of freedom, and the time describe its evolution. Okay. So essentially, this is like so classical field is like classical mechanics degree of freedom, but now with the infinite number of degrees of freedom. Okay. So the classical field theory is like classical mechanics, but now with infinite number of degrees of freedom. Because now you have some finite number of degrees of freedom for each point in space-time. Okay. And the principle of locality also implies that the action for such kind of dynamical variables, so the fields are our dynamical variables, and also implies that the action has a has a local form. So that the action have the form that is always a single space-time integral and some function which is called Lagrangian density, which is a function of the fields, say phi at some point, at the point x, which, and then also its derivatives. Okay. And so because of locality, then the action has a very simple form. Okay. And then you can, as in classical mechanics, you can introduce canonical momentum conjugate to your dynamical variable. So we have momentum density, say conjugate to phi a at each point. Okay, so this is the phi dot, which is the time derivative of phi. And then you can also introduce the Hamiltonian density, which is the pi a, phi dot a. So a is summed and the minus L. Okay, and the Hamiltonian is obtained by integrate this over space. Yeah. And also the equation motion, when you do the variation of the action, then you find the equation motion is given by the following general form. Okay, so the equation motion is given by this general form. And when we study field theory, as we study, say, any other subject, we always start with simplest examples. Okay, and the simplest example would be, say, a single scalar field. Okay, if you can see the single scalar field. Which you have low index, we just have 5, should not depend on space-time point x. And then the simplicity action for such a scalar field, you can just write down based on a general principle, say, yeah, so you can have this form. So we discussed last time the simplest action for scalar field have the following form, partial mu phi, and plus m square phi square. And the sign here is determined because of the metric convention. Okay. So this is the simplest, say, scalar field theory we can write down. Okay, so here I have written here a quadratic function for phi, which we wrote as a general function last time. And here is from here the kinetic term comes from the Lorentz symmetry. So this is the simplest derivative term you can write down, which respect Lorentz symmetry. You can have more complicated terms. You can have this term, for example, square. Okay, but that will be more complicated. So this is the simplest one. Okay. And so this will be the simplest field theory we will study first. Okay, and yeah. So in this case, for this example, the momentum density just equal to phi dot, just time derivative of phi, and then the equation motion is given by a linear equation phi. It's given by that. So this is a very simple theory with very simple equation motion, and but later we will see actually will teach us a lot about general field theory. So that's it's a very quick summary of some of the main points of last lecture. Do you have any questions? Yes. Right. So phi here is a real field. Yeah. Yeah. So phi just take a real value. Yeah. Other questions? Good. Okay. So now we talk about the second topic related to our discussion of classical field theory. It's the symmetries. Conservation rules. So when we have a theory, say with such an axiom, we say the theory has a symmetry. So the definition of the symmetry is the following. So symmetry is some transformation of each field phi A into, say, some function of phi. So this new phi A can say depend on all possible fields. Okay, and so some transformation of your dynamical variables. So here prime is just means a different function, does not mean derivatives. Okay, which leaves the action invariant. Okay. So whenever happens, and we say this is a symmetry. So so for example, in this example, okay, in this example, yeah, let me give you a label to this equation. Let me call this equation star. So in the example of star, say for example the symmetry includes, say, translation. Okay, so if you imagine we take a coordinate transformation, we do a shift in coordinates by a constant shift. Okay, let's imagine we do a constant shift of the coordinates. and A mu is a constant. So A mu are constant. Okay, so it's a constant vector. And now if we assume that the phi transform as the following, so when you change the coordinates, it essentially just change the label, okay, change the label on the field. So, but the value of the field should not change. So that means that the phi evaluated at the original point should be the same. So that means the new transformed phi evaluated at the new point, okay, new x prime point should be the same as the value at the original point. Okay, so this is the yeah. So suppose the phi transform like this. So scalar field should transform as this under a general. So this is the example of a space-time transformation, okay, and the general space-time transformation. As say this equation, okay. So so you change the label, but the value of phi should not change, okay. So the new phi evaluated at the new location should be the same as the value of phi at the original location, okay. And so you can easily check yourself. Okay, so you can easily check yourself. I will not do it here. So this exercise for yourself, that actually this action is invariant under this transform. Is invariant under this transformation with this change of x. Okay. Any questions on this? So second transformation, which this is invariant, is a Lorentz symmetry. So Lorentz transformation is another kind of space-time transformation on the space-time coordinates. Is you take x mu to x mu prime equal to lambda mu nu x nu. So lambda mu nu is the constant Lorentz transformation matrix. Okay. Okay, the constant Lorentz transformation matrix. And again, under such a coordinate transformation, phi will transform this way. Phi should transform this way. And now you can check yourself. Okay, and because of this contraction of partial mu, and this is actually a symmetry. Okay, again, this is left as an exercise for yourself. And in fact, I think in your PSAT problem, you will do something similar. Okay. Any questions on this? Good. So examples like this kind of transformation for translation and for Lorentz transformation. So this is what we call the continuous symmetries. So continuous symmetries okay, so these are the transformations. Yeah, I should also give a label to this equation. So let me call it just star. So continuous symmetries are transformations like star involving continuous parameters. Okay, and so both 1 and 2 and the 2 are clearly continuous symmetries. Yeah, they are continuous symmetries. So you can easily see from here. So here the transformation is A, and A is 4 numbers. Okay, it's a vector. It's a 4 vector, and A can be arbitrarily changed. So it's a continuous parameter. Okay, you can take it to be 0. You can take it to be 0.1 in all directions, etc. So it's something can be continuous changed. And similarly, the Lagrange transformation contains continuous parameters. So do you remember how many continuous parameters does the Lagrange transformation contain? In 4 dimensions. Yes. No. Yes. Yeah, 6. It's because you have 3 rotations, because you have 3 directions, 3 spatial directions, you have 3 rotations, and then you also have 3 boosts. Yeah, so altogether 6. So here there's 6 continuous parameters. And here there's 4. Okay, so here there's 4. So both are continuous symmetries, okay? And in contrast, this Lagrangian this action has a lot of symmetry, which is not continuous. Can you say what that symmetry is? Good. Parity is a good. It's a good answer. Yeah. But there's still something slightly simpler. Yeah. So notice that here it's all quadratic in phi. And what do you observe? So here there's a symmetry, a lot of symmetry. It's phi goes to minus phi, okay, because it's quadratic in phi. And also, of course, there's a symmetry called parity, which in the case x goes to minus x. So the spatial direction x goes to minus x, and then phi again transform as this, okay. And you can also check this is also symmetry. So in both of these cases, they don't involve continuous parameters, and so these are called discrete symmetries. Okay, so there's no continuous parameters, and yeah. In this case, both of them are called Z2. In this, Z2 means that if you do the transformation once, it go back to the identity. Okay, so here if you do the twice, yeah, if you do it twice, go back to the identity. If you do it twice, go back to the identity. This is the same. Okay. So here is a Z2 transformation. Also, symmetries can be also separated into, say, symmetries can be separated into continuous symmetry or discrete symmetries, depend on whether you have continuous parameters or not. But symmetries can also be separated into other different, there's a lot of classification of the symmetry. It's called the gauge symmetry and global symmetries. So they are global symmetries. Corresponding to the transformation parameters are space-time independent. Okay, so both of these are examples of global symmetries because they are just constant. Okay, they don't mu don't depend on space-time, and the lambda don't depend on space-time. Okay, and you can also have local symmetries. Which in which case the transformation parameters are space-time dependent. Okay. So example of the local transformation, which you may remember, is the so-called gauge transformation in E and M. So E and M, you can yeah. Anyway, so later we will see example. We will go back to E and M again, and you will see examples of this local symmetry. Any questions? Yes.
If a transformation changes the action but doesn't change the equations of motion, is that still symmetry?
Yeah. As far as leaves the action, yeah, that's a very good question. So by definition, if it's leave the action invariant, we say it's a symmetry. And in general, actually, almost always, if it leaves the action invariant, actually also leaves the equation motion invariant. Yeah, but it's not guaranteed. Yeah, just purely from mathematical point of view, it's not guaranteed. But for all physical examples, it's almost always the same. Other questions? Okay, good. And now there's a very simple and it's simple, but a very deep connection between the symmetry and the conservation laws. So that may you might have already landed in. Yeah, actually, I forgot when I landed myself. So some of you may land in high school, some of you may land in 801, etc. Anyway, so there's a connection between the symmetry and the conservation laws, and so any conservation laws can be understood as a consequence of symmetry. So in classical mechanics, you may remember that the time translation this leads to energy conservation. And the spatial translation symmetry then leads to the momentum conservation. And if it's a rotational symmetry, then leads to the angular momentum conservation. Okay, so this should be something you already know, say from your classical mechanics. But in classical field theory, this can be generalized. Okay, so here there's a Noether theorem. So first discovered by Noether, the Noether theorem. He said any continuous global symmetry leads to conservation laws. Okay. Okay, leads to a conservation law. And so no matter what kind of symmetry, okay, no matter in addition to those things you are familiar with, but no matter what kind of symmetry, but anytime you have a continuous global symmetry in your system, then you have conserved, you have conservation law. Okay, so now let me give a proof of this Noether theorem. Okay, so before I prove it, do you have any questions regarding its statement? Yes?
So what's the definition? So you said the continuous symmetry is one that depends continuously on a parameter, but if you wanted to write out like equation star in a way that specializes to continuous symmetry, is there a way to do that? To show just how to check something is a continuous.
Oh yeah. You just check whether there's a continuous parameter. You just check whether there's a parameter or not. Yeah. Does this answer your question? Yeah. normally you can just see whether there's a parameter. Yeah. If you write down the transformation explicitly, you will be able to just see. For example, here there's no transformation parameter. You can just see, and there for the Lorentz transformation and translation, you can just see it explicitly. Okay. So important aspect of a continuous symmetry is that because you have a continuous parameter, so you can continuously relate it to identity. So the trivial transformation, you don't transform at all, right? So in this case, the A mu is equal to 0. And so in this case, the trivial transformation, just the lambda mu is the identity matrix. And then you can imagine a slightly turning on a slight infinitesimal rotation or infinitesimal boost. And then that's corresponding to a so-called infinitesimal transformation. Okay. So here you can also just translate A mu a little bit. Okay, so very close to the identity. And so essentially for any, okay, so for any global continuous symmetry, it has an infinitesimal form. Okay, it's just when the parameter, when your transformation parameter is very close to the identity. Okay, very close to the 0. And so for example, for general transformation like this, if the transformation is close to the identity, then we can always write it in the following form. Phi A goes to phi A prime, which is equal to phi A. And with some parameter, small parameter epsilon, and some function Fa, and then say phi B. Okay, and the derivative of phi B, etc. Okay, so this epsilon is the infinitesimal transformation parameter. Okay, so if you have a continuous symmetry, there's always, say, an infinitesimal transformation, which are close to the identity. So this epsilon corresponding to this case would be for A mu is very small, or for the Lorentz transformation case corresponding to rotation angle is very small, or the boost is very small. Okay. Yeah, so the epsilon can be any of those parameters. And then this f, it can be some arbitrary function. Okay, so this f can be some arbitrary functions of your fields. Okay. Good. So in this case, yeah. So in this case, the delta phi. Okay. So the so the symmetry transformation. So we'll use the rotation delta hat phi a. So this symmetry goes then given by say epsilon fa. Okay. So delta hat here implies a symmetry transform, an infinitesimal symmetry transformation. Okay. So now let's consider during a variation of S under this delta hat. Okay, since by definition of the symmetry, because this is a symmetry, that means that delta hat S should be equal to 0. Okay, because the variation of the action should be invariant under the symmetry. And so now let's look at what's the consequence of it. Okay. So now we can just vary this L. Then so this means that the variation of the L, Lagrangian density, must be a total derivative. Okay, since every transformation is proportional to epsilon. Yeah, so epsilon is a small parameter. So when we do the transformation, we only need to keep track linear order in epsilon. So the transformation of the L so must also be proportional to epsilon. Okay, so since this must be invariant, that means the variation of the L must be a total derivative. So K mu would be just some. So for some K mu, okay, for some K mu, so there must exist some K mu, and this K mu can also be 0. In that case, the Lagrangian density is invariant. Yes.
Under the transformation?
Sorry?
Is delta hat the variation under the transformation?
Delta hat is delta hat just denotes such a transformation. Just denotes such a transformation. This is not the general This is not the general variation. This is a very specific. This is a symmetric transformation. And so under the symmetric transformation, your action should be invariant by definition because this is a symmetry, and that in turn, because the S is the integration of L, then that means that the transformation of L, the Lagrangian density must be a total derivative. And here we are only keep track everything linear order in epsilon, and so this must be proportional to epsilon times the total derivative. Okay, and so we must have this structure. Yeah, for some K. Okay, which can be 0. Which can be 0. Okay, good. So now let's look at what's the implications of this equation. Okay, so this equation is the constraint imposed by the symmetry. Okay, now let's look at what the implications of this constraint. So now we can just do the variation of L. Now we can just do the variation of L. Yeah, maybe I will keep that equation. Then I will do this board first. Yeah.
Show if like something is a symmetry of your action for your system.
Yeah.
Would you like directly vary the thing like parameter and then show that your action doesn't change, or would you do that like infinitesimal form and then show that like?
So we want to So we want to use the fact that such a transformation is a symmetry to derive what is the constraint on the Lagrangian. Okay, what is the constraint on the theory? Say we assume that somehow the theory have a symmetry, and then we want to see what is the constraint this put on your theory. Yeah, that's right. We're proving the laws of theorem. Yeah. Good. Other questions? Okay, so that equation is the implication is the constraint imposed by the symmetry, and we want to see what this equation tells us. Okay, and for this purpose, we just do the variation. So the delta hat L. So because L is just a function of phi, and then we have partial L, partial phi A, delta hat phi A, and then we have L partial mu phi A, and then partial mu delta hat phi A. Okay? So we just did the variation. And now, okay, so yeah. And now we are going to use equation motion. Okay, so from the equation motion, I think I erased. Yeah, from the equation motion, then partial L, partial phi A, this is just equal to partial mu, partial L, partial mu phi A. Okay, so we just plug in this into here. So when you plug in this into here, now you notice this becomes a total derivative. Okay, so you have partial L, partial mu phi A, and delta hat phi A. Okay, so you find that after using the equation motion, this variation of L have the following form, which is the total derivative. And this should be equal to the right-hand side, okay? Should be equal to the right-hand side. Yeah, and then here we find, so this should be equal to epsilon partial mu k mu. Okay, so we combine both sides together, plug in that this is equal to epsilon times Fa, and then we conclude, partial mu, partial L, partial mu phi A, then Fa minus k mu, everything equal to 0. Okay? So if we call this J mu, and then we have a conservation equation, partial mu, J mu equal to 0. Okay, so we have a conservation law. So remember, a conservation law is just to have a vector which satisfies this equation, and then yeah. So more explicitly, yeah. So the J mu is just this combination, okay? J mu is just this combination. So any questions on this? Yes.
This like quite a strict condition because it's that the derivative with respect to space-time is 0, but you can have a conservation law from the derivative with respect to time being 0, but not space.
I will. Yeah. This is the stronger version than your normally. Yeah. So this is the space-time version of the conservation law from your normally classical mechanics. Yeah. So this is a field theory version of that. Yeah. I will elaborate that equation a little bit. Yeah. Yes.
So if you only transform the field, not the x and t,
yeah.
The effect is to eliminate that derivative of field of the right?
Say it again.
I mean, the reason that you include the derivative of the field is because you are including the effect of transforming the space-time coordinates.
So here, So here is a general formulation. So this transformation can be general. Doesn't have to be, say, a space-time transformation we said earlier. This is just some abstract symmetry, just some arbitrary transformations.
If you only consider the symmetries that change the field, and not the symmetries.
Yeah, because space-time variable is a dummy variable. In the action, you can always get rid of that. The x change, x is just a dummy variable in your action, because you integrate over x. Yeah.
Higher order derivatives are included.
That can include the normally. You can in principle have as many derivatives as you want, but normally if we have an action which only contains first derivatives, and your symmetry transformation only involves first derivatives.
So we're just not discussing the case of transforming higher.
In principle you can have it. In principle you can have it. Just I'm just writing this for simplicity. Yeah, but maybe you can ask after the class. If it's not clear. Other questions? Okay, good. So let me elaborate a little bit on this equation. So this equation you may have seen in E&M. So which you often call the continuity equation. If you write this equation separately, it has the following form: partial 0 J0 plus partial I or the divergence of the spatial component. So J mu, if we write it in terms of the explicitly, then you have this form. So this is so-called the continuity equation, just the time variation of the density. Okay, the zero component they consider as some kind of density. It's the same as the divergence of the current. Okay, and in particular, you can define a charge, which is the total spatial integration of J0. Okay, so if you integrate both sides by over the total volume, and then this just becomes partial zero Q, and this term become a total derivative, and then you can convert it into a boundary term using the Gauss law, and then normally the current vanishes at infinity, and then you just have the charge conservation. Just have charge conservation. Okay, and yeah. So this is like the field. So normally in classical mechanics, you just have this equation. Okay, and this is the field theory version of your conservation law. Yes.
Can we know what it is, like how to calculate?
Sorry?
Is there a way to calculate what G represents?
J represents?
Yeah, what it represents.
Yeah. If I give you a specific, you will do it in your P set. So if I give you a specific Lagrangian, if you start a specific transformation, and then you will be able to find all those quantities you will be able to find the K explicitly, and you will be able to find all those quantities explicitly, then you can find the J. Other questions? Yes. Right. It's because if we have here, so if we have delta S equal to 0, and then you can just put the delta in, and then this quantity then is integrated over that. If this is 0, then this has to be a total derivative. Other questions? Yes?
It's not a global symmetry where there's this argument break.
Right. Yeah. Good. This is a very good question. So I will not have time to go into here. Let me just very quickly mention. So this is called the first Noether theorem, and when epsilon is space-time independent, and so when epsilon is not space-time dependent, and then the story is a little bit more complicated. So the epsilon will be inside. So the epsilon will be inside this total derivative. You cannot take it out, etc. And then the story changes a little bit, and then there's something called the second Noether theorem. And actually, in that case, when you have local symmetries, when epsilon depends on space-time, instead of finding conservation laws, you find that your equation motion, not all, you find some part of the equation motion are redundant. And if you, it's not difficult, but I actually, in principle, I can put it in the P-set problem. If people really want to see it. Yes?
About the transformation in the vicinity of issuing the identity, what happens to the information of the transformation outside of it?
Good. So this is the key beauty of physics, which you may already have seen in quantum mechanics. So whenever we see a symmetry, no matter how complicated that symmetry is, say some continuous symmetry, it's enough just to understand that symmetry near the identity, near the to be the infinitesimal transformation. It's because any finite transformation you can build up from just adding up the infinitesimal transformations. So once you know the infinitesimal transformation, actually essentially up to some global topological structure, essentially determine the full finite transformation. Yeah. No, it's always a symmetry, right? Because because each step is a symmetry, and so you add them up, still a symmetry.
Okay, but a sequence of different symmetries.
Or if you do different, yeah, there's still a symmetry. Yeah, because by definition, if something transform is invariant, you do a lot of transformation, it's still invariant. Good. Other questions? Yes.
For discrete symmetry, we don't have this epsilon. Can we do something similar?
Sorry?
For discrete symmetries.
For discrete symmetry.
We have to do this analysis, but can we do something similar?
Yeah, in general, for discrete symmetries, you don't have such a conservation law. You don't have such a conservation law. Sometimes you can still define some discrete quantum number, which is conserved, like the parity, which in the parity case, and but you don't have a current. Okay, so here J mu is called the conserved current. So but you won't have a current. Good. So this concludes our discussion. Very quick discussion of the important features of classical field theory. And with this preparation, and now we can start talking about, start thinking about going to quantum mechanics, talking about the quantum fields. Okay, and so here is a good place to pause a little bit from what we said, from what we already said about the classical field theory, to anticipate a little bit about the quantum field theory. Okay, so here I will restate our goal for quantum field theory, which I said a little bit in the last lecture. Okay. So now we have seen the classical fields, and our goal is to understand the quantum version of this story. Okay. So classical field theory is the classical mechanics with infinite number of degrees freedom, and now we want to quantize this infinite number of degrees freedom, and now this becomes quantum field theory. Okay. And now we want to understand the quantum dynamics of such a field, such kind of 5 fields. Okay. And for example, example is the E&M. We have electric magnetic fields. Okay. And you know the Maxwell equations. You can solve the Maxwell equations. And so that defines the classical field theory. And then we will tell you how to actually quantize such a system to understand the electric field and the magnetic field quantum mechanically. Good, and that actually would be our goal. Okay, so we will start the simplest field theory, just the scalar field theory, and then we go to the Dirac theory, which describes the electron, and then eventually we will go to the theory which describes the electromagnetic field. So this is called the QED. Okay, quantum electrodynamics. So that will be the end point of this course. Okay, so now let's say a little bit how we go to this classical field theory to quantum field theory. Okay, so some general remarks. So before doing that, let's think a little bit how we go from classical mechanics with a small number of degrees freedom, how you go to quantum mechanics. Okay. So so let's recall. So in classical mechanics, so let's just consider the simplest case. You just have a single degree freedom, say xt. Okay, just one-dimensional particle whose motion just describes the xt. And then of course the goal of classical mechanics is just to solve the equation motion over xt. Okay, so if I write down the equation for xt and I solve it, then I'm done. Okay, I'm done. You solve the classical mechanics. So when we go to quantum mechanics, what do? So this xt then become an operator. Okay, so become an operator. So a classical dynamical variable now become a quantum operator. And the equation motion of xt, if you remember, then do you remember what it becomes? Yeah, exactly, become the Heisenberg equation. So become the Heisenberg equation for xt, for this operator xt now. Okay, yeah. So in quantum mechanics, there are normally two ways to describe it. So first is the Schrodinger picture. In this case, you have a wave function, which is a function of x and t, and then you have an operator which is x. Okay, and then of course you also have conjugate momentum, etc., which is defined to be, say, x dot. Okay, and so the wave function is a function of the eigenvalues of. So x here should be understood as eigenvalues of this operator x hat. Okay, it's the eigenvalue of x hat. So in the Schrodinger picture, you solve the evolution for psi. You solve the equation for psi, and once you find psi, then you can calculate any quantities you want. Okay, you can calculate any expectation values, any amplitude, etc. But the second way of approach it is the Heisenberg picture. In this case, the dynamical quantity is your operator. Now you assume the operator depends on time. So in the Schrodinger picture, your x is just some constant operator does not depend on time. But in the Heisenberg picture, now your operator now become time dependent. Okay, and the equation motion, and you solve the Heisenberg equation. Okay, and then the state is invariant. Okay, state does not evolve with time. Okay, so you solve the Heisenberg equation for those operators, and once you solve the Heisenberg equation, and then you can evaluate again your expectation value in any states you are interested in, etc. Okay. So any questions on this? So this is a very quick review what you did to go from classical mechanics to quantum mechanics. Okay. So now in field theory, okay, in field theory we do the same similar thing. So similarly, in field theory, we have classical fields. Okay, we have classical fields. And then when you go to quantum, this become quantum operators. Okay, so this is now quantum operators. Remember, in field theory, this x is always just labels of the space point. Okay, it's not a dynamical variable. Okay, the rotation is a little bit. Yeah, here in classical mechanics, this is dynamical variable, but in field theory, this is just labels. Okay, so they're not dynamical. A dynamical variable are phi itself. So phi become an operator. Okay, and then now the classical equation motion of phi, which will be derived and then become the Heisenberg equation. Phi hat. Okay, for phi hat. So again, here you can do two pictures. You can do the Schrodinger picture, you can do a Heisenberg picture. So for QFT, the Schrodinger picture, again, you look at the wave functions of your dynamical variables. the eigenvalue of dynamical variables. So what's the generalization of this psi xt? So remember here, psi is a function of eigenvalue of your dynamical variables, okay? So now if we push this analog further, when you go to quantum field theory, in the Schrodinger picture, now the wave function should be a function of phi x and t. Okay, so this phi x are eigenvalues of phi hat x. Okay, so in the Schrodinger picture, phi hat does not evolve with time, and so you have the wave function, which is the function now become a functional a bit, because this itself is a function of space. Okay, and yeah, and you solve the Schrodinger equation for this, and then you have the operator. And then you have the operator, yeah, and so you have and the dynamical, and then you have operator phi x. Okay, so that's what you do in the Schrodinger picture. In the Schrodinger picture, and in the Heisenberg picture, if you forget about the wave function, okay, you look at the evolution of operators. So the Heisenberg for the field theory, the Heisenberg picture for the field theory is that you look at the evolution of x and t. So now this just obeys the Heisenberg equations, which is just the classic, just the quantum version of the classical equation for phi. So you have the you look at the evolution of this, and then the state does not change with time. Okay. The state does not change with time. Good. Any questions on this? Yes. Yeah. So in the Schrodinger picture, so remember the x is a label for phi, but time is evolution. But in the Schrodinger picture, the operator don't evolve. And so there's no time here. So we don't have time here. And we just have the analog of the x here in the Schrodinger picture for the classical, for quantum mechanics. And then the time dependence is in your wave function. So the wave function is a function of possible values, eigenvalues of this operator phi now. Okay? And then the Heisenberg picture, again, then you just focus on the operator equations. And once you solve the operator equations, and then you can calculate the, say, excitation values in any state you want. Okay. So now you can already maybe see a difference a little bit. So if you do the Schrodinger picture, you have to deal with this beast, okay? Which is the wave functional of all possible values of some function in space, okay? And if you have multiple fields, then this is a hugely complicated thing. And you need to write down the Schrodinger equation for it, etc. Okay? But in the Heisenberg picture, we just solve the analog of the classical equation of motion, which we have already written down. And you just now interpret it as a quantum operator equation. So which one you think is simpler? So that's why in quantum field theory, we almost always use Heisenberg picture. Okay, we always use Heisenberg picture, and we don't even rarely think about the wave function. Even though sometimes this can be useful in some problems, but for the most of the time, this is much easier. Okay, so that's what we are going to do. Okay, and so in quantum field theory, we will just use the Heisenberg picture almost all the time. Okay? From now on, I will not talk about the Schrodinger picture. Okay. Good. So it's very important you remind yourself about quantum mechanics in the Heisenberg picture. Okay, and because most of your quantum mechanical classes before, maybe it's all in the Schrodinger picture, solving the solving the Schrodinger equations, etc. But now you have to change the perspective to think everything in terms of the Heisenberg picture, and then that will make you learning quantum field theory much easier. Okay. Good. Any questions on this? Yes.
So in the Heisenberg picture, if we're not concerned about the wave function and all, then how do we determine, like, for example, the probability or the expectation value of where x is at some point for the momentum?
Good. That's a very good question. So this is actually also related to the kind of questions we want to solve in quantum field theory. So in quantum field theory, we often work with the vacuum state. So for example, here, so when you consider the QED, most of the time in the quantum electrical magnetic field, they are in the vacuum state. And so we just consider the psi in the vacuum state. And so we don't have to consider, so normally in quantum field theory, they are preferred states we are interested in. But that's another reason that the Heisenberg picture is convenient. Yeah, you don't have to consider general state in general. Yes.
What is the physical meaning of the wave function of the state here?
Sorry?
What is the physical meaning of psi here?
Oh, this is just some state you are interested in. Still, you have a Hilbert space, but now you just don't. When you study the evolution, you only evolve operator, you don't evolve states. Yeah, so that's the difference between the Schrodinger and the Heisenberg picture.
But for example, in quantum mechanics, we take the expectation values of some operators with respect to the state, and we get like measurements, the result and stuff. So what about here?
Yeah, it's the same thing. Yeah, same thing. Yeah, at this level, there's no difference between quantum field theory and quantum mechanics. Yeah, just think about quantum mechanics in terms of Heisenberg picture. Translate everything you learned about the Schrodinger evolution, etc., in terms of Heisenberg picture. Yes. Yeah, that's right. Yeah. Yes.
But if the state we're interested in is generally the vacuum state, then like what sorts of measurements?
Yeah. So it's again. So yeah, it's a very good question. What I should have said is that what the state we are interested in are states which are close to the vacuum states. So you excite the vacuum a little bit, and it's not. Yeah, of course, in the vacuum you don't have anything, and we are things close to the vacuum state. Yeah, and later when we discuss things, you will see. Yeah. Good. Okay. So before going to quantum field theory, let's also make some remarks, have a short discussion on relativistic quantum mechanics. Okay. So naively, if you have special relativity, plus quantum mechanics, so if you want to generalize, so most of the quantum mechanics you learned is the non-relativistic quantum mechanics, okay? But now if you want to incorporate we want to combine the special relativity with quantum mechanics, and then what should you get? What do you think you should get? I expect. Yeah, just whatever come to your mind. That's the right answer. That's the correct answer. But I was hoping some of you will say it's relativistic quantum mechanics. Okay. So naively, when you combine these two, in particular, if you read some old quantum mechanics books, they do discuss relativistic quantum mechanics. Okay, so naively, that's what you get. Okay, when you combine these two, and you say, oh, we just get relativistic quantum mechanics. Okay, but that's actually not the correct statement. Actually, strictly speaking, the reason now you don't actually learn much about the relativistic quantum mechanics because, strictly speaking, relativistic quantum mechanics does not exist. Okay, and whenever if you want to combine quantum mechanics with special relativity, actually you get the quantum field theory. So the quantum field theory is actually forced on us if you want to unify special relativity and the quantum mechanics. Okay, and even if you don't want to talk about the fields, okay, even if you don't want to talk about field, if you just want to talk about particles. Still, if you want to unify these two, then you actually automatically leads to quantum field theory. So now let me just explain why this is the case, okay? So that you have some better appreciation of the quantum field theory. Good. So let's try to apply what you did for non-relativistic quantum mechanics. Try to generalize it to derive some relativistic quantum mechanics. Okay, suppose you are the people in the 1926. Okay, quantum mechanics just was discovered, and you say, oh, people have understood non-relativistic quantum mechanics. Now let's generalize to special relativity. Okay, so in non-relativistic quantum mechanics, how do we derive the Schrödinger equation? The way we do this is we start with a dispersion relation, okay, for a non-relativistic particle. And then we say let's take E to I partial t, okay, P. So say if you can have a vector become, yeah, so let me forget about H bar. Just P then becomes spatial derivatives, and then this equation just becomes the Schrödinger equation for the free particles. Okay, so this becomes the Schrödinger equation for free non-relativistic particles. Then you can add the potentials, etc. Okay, so that's how you derive your Schrödinger equation for non-relativistic quantum mechanics. So, but if you are someone, say, in the early days of quantum mechanics, say, now let's try to generalize it to special relativity, and then it's easy to do. Then in the relativistic case, then you just start with the relativistic dispersion relation. Okay, you say let's do the same thing. Okay, let's do the same thing. So this become I partial t, and this p become this one, and then we can just write this equation. Okay. So now let's combine this derivative together, or put all this on the same side. And then what you find is partial mu, partial mu. Okay, that's what you get. So does this equation look familiar? Okay, so this is the simplest scalar field theory equation motion we have written down. But here the interpretation is very different, okay? So earlier we wrote down this equation, we say this is Klein-Gordon equation. This is the Klein-Gordon equation. Okay, so this is the equation motion for the simplest free field scalar field theory we wrote down before. But here the interpretation is very different. So remember, the psi is not a field in quantum mechanics; it's a wave function for a single particle sitting. So the psi is the amplitude for particle at spatial location x at time t. Okay, so this is, and it's square, then it's its probability. Okay, and this does not describe a field. Okay, this is the wave function of a single particle. Okay, even though they have the same equation as the field theory we wrote down earlier. And so that's what Klein-Gordon did. Okay, so the Klein-Gordon, they tried to generalize non-relativistic quantum mechanics, relativistic quantum mechanics, and they wrote down this equation. They say, oh, now we are immortal, okay, because we wrote down the first equation for relativistic quantum mechanics. And then soon realized. So soon realized actually this equation, if you want to interpret it as a equation for the wave function, there are actually lots of problems. There are various problems. By saying lots of it, maybe it's a little bit exaggeration. There are various problems. So let me call this equation. I think I have used up my stars. I think to have a 4 star is a little bit too much. Let's just call this equation 1 for this section. So some immediate difficulties. Of interpreting one as a wave equation, okay? As a wave equation for relativistic particle. Yeah, let me just save time. Okay, so this is the wave equation for non-relativistic particle. If you want to generalize to quantum mechanics, relativistic quantum mechanics, then you would interpret this as a wave equation for a single relativistic particle. Okay. So first is that, so if you remember, so in this equation, okay, for if you go back to your early days of this non-relativistic quantum mechanics, so you remember from this equation you can derive an equation for the conserved probability, okay, conserved probability, and that equation tells you that psi squared should have the interpretation of the probability. Okay, so but for that equation, you can show there's no quantity there's no quantity can be used as probability density. Okay, so probability density by definition should satisfy 2 conditions. So the first condition is that it's non-negative. And the second condition is that it should be conserved. Okay, the probability should be conserved, otherwise you violate the So you can show that this equation actually does not allow. This equation allows such a quantity, but this equation does not allow. Okay, and I will not go through that by itself, I think that will be in your P set 2. Okay, that will be in your P set 2. You will show it yourself. And the second difficulty is that if you square that, if you find the energy, so the energy, if you take the square root, then the energy in principle can be, say, plus minus. You have two solutions. Okay, E equal to plus minus this quantity. So in contrast to that equation, there's only positive energy. Okay, non-relativity just have positive energy. So classically, you can just say, let's throw away the second branch. Okay, we can just throw away the second branch by hand. Okay, classically, but quantum mechanically, okay, so classically, just ignore the second branch. The lactive branch. Okay, but quantum mechanically, this is not possible. Okay, because you have the equation there, then you automatically have the lactive solutions. Okay, so quantum mechanically, and then you have dispersion relation like this. So that dispersion relation has the following form: is phi E as a function of P. Okay, so you have a positive branch, then you have the lactive branch. And then you remember in quantum mechanics, you can have the then you have energy levels. And you have energy levels. And such particles, then a particle here, then have a higher energy than particle here. Okay, and so here the energy level is higher than energy level here. And there's always a non-zero probability quantum mechanically for a particle to go from some higher energy level to the lower energy level. Okay, just like in the hydrogen atom, if you excite it, and they always go to the lower energy level. So in quantum mechanically, such thing cannot be avoided. Okay, so you cannot just throw this branch away. Okay, and so this will lead to instability. Because the energy can be infinitely lactive. Okay, can be infinitely lactive, and then all your particles will all go to infinitely lactive energies, and then your system will be in big problem. Okay. So these are the two. So these are the two the most prominent problems, and then people tried many different ways, tried to avoid them, etc., including some very ingenious solutions, etc. So we will not go into them. But let me just mention, there's actually, even if you can address those problems, still the relativistic quantum mechanics will not make sense for a very fundamental reason. Okay, so these are the more like superficial reason why that equation does not quite work. Okay, but there's actually more fundamental reason why relativistic quantum mechanics, even as a concept, does not make sense. Okay. So by definition, if you want to interpret this kind of thing as a wave function, okay, so what's the interpretation of the wave function, which we already said? So this is describe the amplitude for single particle at some point, okay, at some point x at time t. But now if you have two particles, what do? You introduce the location for particle 1 and particle 2 and t. Okay, so this describes two particles. And if you want to describe three particles, then you have to introduce more x. Okay, remember that's what you did in non-relativistic quantum mechanics. So in non-relativistic quantum mechanics, this makes sense. Okay, you can just, because there's no mixing between the different branches, say single particle, two particles, because particle cannot be created and destroyed in a non-relativistic system. But in relativistic system, you can always create particles. Okay, if you have enough energy, you can create new particles, pair create electrons, okay, happens in the accelerator all the time. All electrons, they can annihilate into photons, okay? So the particles are not conserved, okay, not conserved. So this kind of wave function concept don't even make sense. So if you want to describe, so that means whenever you have special relativity and the quantum mechanics together, you must have a framework which can describe arbitrary number of particles at the same time, okay? Because particle numbers can change all the time, okay? Because of annihilation and the creation effect. And that cannot be achieved by this kind of concept like wave function, okay? Cannot be achieved by wave function. It turns out, miraculously, that can be achieved by field theory. It turns out the field theory, once you quantize it, automatically give you a framework to describe arbitrary number of particles, okay, in the unified manner, okay, single particle, two particles, arbitrary number of particles, and so this is one of the magic of field theory. So that's why the field theory plays such an important role in particle physics. It's because the excitations of fields automatically provide the mechanism to describe arbitrary number of particles. Okay, so we will stop here today.